Namaste. Welcome to the lecture series on the subject Basic Thermodynamics, Module 5, Part 1, Ideal Gases, Lecture number 5. Myself, Dr. Satheesh Kumar, Associate Professor of Mechanical Engineering, Canara Engineering College, Bantwal. So the contents for this topic are change in entropy, evaluation of change in entropy in various quasi-static processes, air-water mixtures and related properties. Change in entropy. Now let us consider a process taking place from state 1 to state 2, and the initial property values, let it be P1, V1, T1 and S1. They are nothing but the pressure, volume, temperature and entropy, and final conditions are P2, V2, T2 and S2. So this is after some addition of heat. Now all of us know the first law of thermodynamics, dq is equal to, or del q is equal to del w plus du, and for the boundary work, involvement of only boundary work, del w you can write as pdv, so the equation you can rewrite it as delta q is equal to pdv plus du. Also by definition we know that change in internal energy du is equal to cv into dt. So if you substitute, so you will get del q is equal to P dV plus Cv dt. Now divide this equation by temperature, so then you will get del q by T is equal to P into dV by T plus Cv into dt by T. Now as all of you know, del q by T is nothing but the term change in entropy, so that is ds. So you can substitute that and you can rewrite the expression as ds is equal to P by T into dV plus Cv into dt by T. Now for a perfect gas equation, for unit mass you have PV is equal to RT, or P by T is equal to R by V. So replace P by T in the first term on the right hand side, so you'll get ds is equal to R by V into dV plus Cv into dt by T. Now you have to integrate this to get the change in entropy. So you will get integration from 1 to 2 ds is equal to integration R into dV by V plus integration Cv dt by T. Now here R is constant, so integration of 1 by V is nothing but ln V, and here Cv is constant, so integration of 1 by T with respect to dt is 1 by ln T. So here you can write the change in entropy as S2 minus S1. R is constant as I told you earlier. Integration of 1 by V with respect to dV is ln V. If you apply the limits, so it will be ln V2 minus ln V1, that is nothing but ln V2 by V1. Similarly here you will get Cv into ln T2 by T1. So this equation, this is one of the important equations for change in entropy of any gas. Okay. Now this equation can also be expressed in terms of pressure and volume. So here you can see it is expressed in terms of volume and temperature. So here to find out change in entropy, you need the volume at state 1 and state 2 as well as the temperature at state 1 and 2. Now let us see if this expression can be expressed in terms of pressure and volume. So we have P1 V1 by T1 is equal to P2 V2 by T2. So from this you can write T2 by T1 is equal to P2 by P1 into V2 by V1. So rewriting this expression. So here you can see the second term in equation 1 is T2 by T1. So it can be replaced as P2 by P1 into V2 by V1, and if you substitute and if you simplify, so you will get S2 minus S1 is equal to Cv plus R. Now here what happens is Cv ln, now in place of T2 by T1 here in equation 1, when you substitute P2 by P1 and into V2 by V1, it becomes Cv ln bracket P2 by P1 into V2 by V1. So now CV ln P2 by P1 into V2 by V1. So you can separate the terms ln P2 by P1 plus ln V2 by V1. So CV is common, right? So there are two terms now, ln CV ln P2 by P1 and CV ln V2 by V1. So CV ln V2 by V1, and here already one R ln V2 by V1 is there. So if you can add those two terms, so you'll get CV plus R ln V2 by P1, and the remaining term is this, that is CV into ln P2 by P1. So I request all of you to write and simplify this expression. So then you will get this equation. Okay. Okay, now you know that Cp minus Cv is equal to R. That is Cv plus R is equal to Cp. So if you substitute for Cv plus R as Cp, so you will get S2 minus S1 is equal to Cp ln V2 by V1 plus Cv ln P2 by P1. So here the change in entropy is expressed in terms of volume and pressure. So you can see V2 by V1 final volume and initial volume, P2 by P1 final pressure and initial pressure. Now the equation 1, not this equation, equation 1 can also be represented in terms of temperature and pressure. For that, once again you have to go to the basic equation, P1 V1 by T1 is equal to P2 V2 by T2. If you simplify or rewrite this, you will get V2 by V1 is equal to, okay, it's not P2 by P1, it should be P1 by P2. So all of you make a correction here. So it is P1 by P2 into T2 by T1. Now let us substitute it in equation 1. So you will get S2 minus S1 is equal to R. So now in place of V2 by V1, you are substituting P1 by P2 into T2 by T1, and this term as it is. So now what you will do is you have to split this first term R ln P1 by P2. So you can write as R ln P1 by P2, right? And the second term as R ln T2 by T1. R ln T2 by T1. So you take a sheet of paper and do it, okay? T2 by T1. Okay, write properly. Now, and the one more term is there, plus Cv into ln T2 by T1. ln T2 by T1. Now what you have to do is for this second term R, so R is nothing but Cp minus Cv. So you substitute this only for this term. I'll show you. This term you have to substitute as Cp minus Cv, R as Cp minus Cv. So what happens is you will get again two terms, Cp into ln T2 by T1, right, minus Cv into ln T2 by T1. Try to understand this. In place of R, if I substitute Cp minus Cv, you will get two terms. One is Cp ln T2 by T1, other one is minus Cv. So minus Cv ln T2 by T1 gets cancelled with this. So what will remain? R ln P1 by P2 plus Cp ln T2 by T1. Okay. So if I write that Cp ln T2 by T1, this term here from here, Cp this into ln T2 by T1, this term, first term. Second term is plus R ln P1 by P2. But if I take the reciprocal of P1 by P2, it becomes P2 by P1. Then this plus sign becomes minus here. So it becomes minus R ln P2 by P1, because it is ratio is written as always as the final divided by initial. So to make it P2 by P1, we have taken the reciprocal of P1 by P2. So then it becomes minus R. Okay. So better you take a sheet of paper and simplify and find out this. Okay. Now let us evaluate the change in entropy in various quasi-static processes. So let us begin with the constant volume process. So as all of you know the first law equation, del Q is equal to del W plus du, and for a constant volume process del W is equal to 0. So we'll get del Q is equal to du, but as all of you know, du, the change in internal energy, is nothing but mCV dt. Now to get entropy, you have to divide this by T. So del Q by T is equal to mCV dt by T. Now to find out the change in entropy, the first term or the term on the left hand side, that is del Q by T, is nothing but the entropy term. So you have to find out change in entropy. For that you have to integrate this. So integrating, so you will get integration from 1 to 2 del Q by T is equal to integration 1 to 2 mCV dt by T. So you can write this as S2 minus S1. Here mCV is constant. So integration of 1 by T with respect to dt, and if you apply the limits, you will get ln T2 by T1. So this is the expression for change in entropy in case of a constant volume process. Now coming to the constant pressure process, as usual del Q is equal to del W plus du, and for a constant pressure process del W is equal to PdV, right, the boundary work. So PdV, so P you can substitute as PdV you can substitute as mR dt, and du as mCV dt. So it becomes m into R plus Cv into dt. So R is nothing but Cp minus Cv. Sorry, it's a mistake here. It's just a small dt. Okay. So you can write del Q is equal to mCp dt. So I think this already you studied somewhere in previous modules. Now you divide it by T. Once again del Q by T is equal to mCp dt by T. Once again you have to integrate this. So integration from 1 to 2 del Q by T is equal to integration from 1 to 2 mCp dt by T. So you'll get S2 minus S1 is equal to mCp ln T2 by T1. So this is the expression for the change in entropy, right, for a constant pressure process. So for constant volume process mCV ln T2 by T1. For constant pressure it is mCp ln T2 by T1. Okay. Now coming to the isothermal process, once again going to the first law equation, del Q is equal to del W plus du. But for the isothermal process, since there is no change in temperature, change in internal energy is 0, because as all of you know, internal energy is purely the function of temperature. If the temperature remains constant, so then there is no change in internal energy. So you will get del Q is equal to del W. So for an isothermal process, as all of you know, del W, or the expression for work done, is nothing but P1 V1 ln V2 by P1. So now if divide it by T, you will get del Q by T is equal to, also you can substitute for P1 V1 as mRT1 divided by T, that is T1 ln V2 by V1. So you will get, after integration, S2 minus S1 is equal to mR ln V2 by P1. Okay. So this is the expression for the change in entropy in case of isothermal process. Now coming to the reversible adiabatic process, del Q is equal to 0 for the reversible adiabatic process. Therefore, there is no question of change in entropy. So S2 minus S1 is equal to 0. Since the reversible adiabatic, another name for that is isentropic. Isentropic in the sense entropy remains constant. That means entropy at the final state is equal to entropy at the initial state. So S2 is equal to S1. Hence the process is called as isentropic. Okay. Now coming to the polytropic process. So we know that for a perfect gas, del Q is equal to gamma minus n by gamma minus 1 into del W. The delta W is nothing but PdV. Okay. So dividing by T, you will get del Q by T is equal to gamma minus n by gamma minus 1 into PdV by T. So integrating, so integration from 1 to 2 del Q by T, gamma minus 1 by gamma minus 1, integration of 1 to 2 PdV by T. Also we know that PV is equal to RT or P is equal to RT by V. So if you substitute, you will get S2 minus S1 is equal to gamma minus n by gamma minus 1 integration from 1 to 2 RT by V into dV by T. So simplifying, R is taken outside, T gets cancelled here, this T gets cancelled with this T, R is taken outside, it is integration from 1 to 2 dV by V, which is nothing but ln V2 by V1. Now this is the expression for change in entropy in case of polytropic process. Now let us study the air-water mixtures and related properties. In fact, this is a big topic on psychrometry. Since it is connected to real gases, ideal gases, so they included a small topic under this module just to go through the few definitions for the air-water mixtures. So the study of properties of air and vapor pertaining to air conditioning is called as psychrometry. So this is the big topic which I mentioned just now, which you are supposed to study in detail in the next semester subject, applied thermodynamics. So anyhow we are going to deal with in detail there. So just to go through let us go through the basics. So what is the definition of dry air? It is a mixture of nitrogen, oxygen and small percentage of other gases. So air contains, as all of you know, 79% nitrogen, 21% oxygen by volume. Suppose if we take on mass basis, it will be 73% and 27%. Okay, and it has a molecular weight of 29. So usually molecular weight, it is a molecular weight of oxygen and nitrogen contributing to the molecular weight of air, because the rest of the percentage of the rest of the gases is very small. Now what is moist air? It is a mixture of dry air and water vapor. So whatever the air present in the atmosphere, so usually it will not be completely dry, it will be moist air, because there will be a small percentage of moisture present in that air. So the amount of water vapor varies according to the temperature of air and reaches saturation at one point. This is very important. The amount of water vapor or the moisture in the air, so that purely depends on the temperature of the air. Okay, and also so there is a saturation point. Till then you can or the moisture can be induced into the air. Now what is saturated air mixture? Saturated air mixture is a mixture of dry air and water vapor, that means it is moist air, in which the partial pressure of vapor is equal to the saturation pressure of water at the temperature of the mixture. Now you see, this is very important term to understand. So here saturated air mixture is a mixture of dry air and water vapor. Okay, that is nothing but the moist air. So here when a moist air is there, the total pressure of that air is nothing but P is equal to P of air, that is dry air, plus P of the moisture. Usually we write it as vapor, we write it as P suffix V. So this is from the Dalton's law of partial pressures. Atmosphere pressure P is equal to PA. Okay, for this A, okay, try to understand this. This is atmospheric or air, this is small v, vapor. Okay, so PA plus PV. Now here if the air has to be called as saturated air mixture, the partial pressure of the vapor, that is PV, should be equal to the pressure of water at the temperature of the mixture. Now here this dry air and water vapor, that is moist air, is in certain temperature, at certain temperature, is at certain temperature. Now go through the steam tables or thermodynamic data handbook and check the saturation pressure for this temperature. See, you have given the atmospheric temperature, go through the data handbook or the steam table, find out the pressure, saturation, there is a column saturation pressure, right? Maybe table A1 or A2, just confirm that if you open the table, steam tables, and there you can find the pressure, saturation pressure corresponding to this temperature. If that pressure is equal to the partial pressure of water vapor, that is PV, then it is saturated, right? Because air is saturated because it has absorbed the amount of air which it can amount of moisture which it can absorb. Okay, so this is very important definition. Okay, now what is unsaturated air mixture? Previously you studied saturated, where the partial pressure of water vapor is equal to the saturation pressure at the mixture temperature. Try to understand this. Partial pressure of water vapor PV is equal to saturation pressure, means it is saturated. Partial pressure has been saturated, so that is why it is called as saturated. Now unsaturated means here it is a mixture of dry air and superheated water vapor. So what do you mean by superheated water vapor? If the temperature of water vapor is above the saturation point, so then it is called as the saturation, superheated vapor. So saturation means what? The boiling point. So liquid water, when it reaches the saturation point, means it starts boiling and it starts converting from water to liquid to vapor. Okay, so finally saturated liquid vapor it becomes, and further heating it leads to superheated vapor. So the temperature of the vapor will be above the saturation temperature. So here it should be a mixture of dry air and superheated vapor. So temperature of the vapor should be more than the saturation temperature. So what is the condition then? The partial pressure of the vapor is less than the saturation pressure. PV, here previous case PV is equal to PS, here PV is less than PS. Now you see PV is less than PS. Now PS is the corresponding to the temperature of the mixture, that is T, actual temperature of the mixture. Okay, now if you observe the steam table, this PV, since PV is less than PS, so you will get the temperature of the vapor less than the temperature of this, means according to the partial pressure, the temperature at the partial pressure of vapor is less, but actual temperature is more. That means it has already crossed the temperature, saturation temperature, right, and it is reached the superheated state. So here partial pressure of vapor is less means the temperature at partial pressure of the vapor is less, that is T, but your actual temperature is always more, is already more, right? So in that case you call it as superheated vapor, because your this temperature is more than the this temperature, right? So this is the temperature corresponding to the partial pressure of vapor T, maybe 10 degrees Celsius, but your actual air temperature is 20 degrees Celsius, so air is superheated, water is superheated. So water, that you see I am talking about only vapor part here, I am not talking about complete air, I am talking about only vapor part. So vapor is superheated. The condition is PV should be less than PS. Okay, so try to understand to some extent. Anyhow, once again this subject, this topic will be discussed in ATD in the next semester. Okay, now coming to the one more definition, that is super saturated air mixture. So now all of you can tell what is the condition here. So here PV should be greater than PS, right? So PV is greater than PS. Now if PS is corresponding to the temperature of the mixture, since PV is greater than this, so this temperature is more. Okay, the temperature corresponding to the partial pressure of vapor is more. Okay, so then this is not yet become superheated, that or saturated, not yet reached the saturation point. So then, so this is called as the super saturated air mixture. It's a mixture of dry air and just water vapor. It's just water vapor, it's not saturated yet. So in which partial pressure of the water vapor is greater than the saturation pressure at the temperature of the mixture. So saturation pressure, so this pressure you will find out from the temperature of the mixture. So the temperature of the mixture is less than the temperature at the partial pressure of the water vapor. So it is super saturated air mixture. For the superheated, what is the condition? The actual temperature should be more than the temperature at the partial pressure. but here it is not the case. The temperature, actual temperature is less than the temperature at the partial pressure of the vapor. So this is, the temperature is not yet reached TV. You see, this temperature T is not yet reached TV, means it's not yet reached the saturation. So that is just the water vapor. Okay. Now we'll discuss the few temperature terms involved in this. One is the dew point temperature. So this is nothing but the temperature when the unsaturated air is cooled. Unsaturated air is this one, top one. Unsaturated air is cooled. So unsaturated air, what is the condition? The vapor is in superheated state. So superheated means it is above saturation. So if you cool this, the temperature of the water vapor decreases and it reaches the saturation point. So at the saturation point, if you cool a vapor, it starts condensing. So the formation of a dew takes place. So that is what, when an unsaturated air is cooled at constant pressure, the mixture reaches the saturation temperature, because initially it's the water vapor superheated, no? So temperature is more than the saturation temperature. So corresponding to the partial pressure of the water vapor, the temperature at which the condensation of the vapor begins, resulting in the formation of liquid droplets or dew, and it is called as the dew point temperature. So simple, I will explain in simple terms. Unsaturated air, in case of an unsaturated air, the water vapor is superheated. Okay, now you start cooling this, so the temperature reaches the saturation point. The moment temperature of the water vapor becomes equal to the saturation temperature, it starts condensing, forming dews or the water droplets or liquid droplets. At this corresponding temperature at which this dew formation or droplet formation takes place is nothing but the dew point temperature. Okay, next is absolute humidity or specific humidity or humidity ratio. This is nothing but mass of vapor to the mass of dry air. So it is a simple terms, mass of vapor. So in air, as I told you earlier, it is a mixture of dry air plus water vapor. So mass of water vapor to the ratio of the mass of water vapor to the mass of dry air is called as absolute humidity or specific humidity or humidity ratio. It is given by omega is equal to mv by ma. Now coming to the relative humidity, it is defined as the ratio of partial pressure of water vapor in a mixture to the saturation pressure of water at dry bulb temperature. So relative humidity, so in relation to the saturation point, what is the humidity? So for that you have to compare or you take the ratio of the partial pressure of the water vapor, that is PV in a mixture, to the saturation pressure, that is PSAT or PS at the dry bulb temperature. So now again a new term has come into picture, dry bulb temperature, which I am going to explain now. Okay, so relative humidity is PV divided by PS or PG also you can take. Okay, some books they take PG in place of PS, P saturation. Okay. Now coming to the last part of this topic, dry bulb temperature. It is the equilibrium temperature of the mixture indicated by an ordinary thermometer and denoted by T suffix dB. Ordinary thermometer. Temperature indicated by that is the dry bulb temperature. Then what is the wet bulb temperature? It is the temperature indicated by a wet bulb thermometer which has its temperature sensitive element, that is the bulb, covered with the wick soaked in water. It is denoted by TWB. So here now this is the dry bulb temperature measured by an ordinary thermometer. You can see it is ordinary thermometer, but in case of the second case you can see the bulb is covered with the wick and it is constantly or continuously soaked with water. For that what you have to do is you have to cover this with the wick, and that bottom part of the wick has to be dipped in a water small container with water, so that entire wick always in wet condition, and whatever the air which is passing through the wick reaches the bulb, so it will be saturated, and for the temperature corresponding to that is called as the wet bulb temperature. Okay, this is about the theory part of this module 5 part 1 ideal gases. So with this I conclude this lecture number 5, and we'll start solving the numericals in lecture number 6. Thank you.